Hi dear friends, this is Bhusab Sonani, Assistant Professor, Department of Chemistry, Gokhale Education Society's Arts, Commerce and Science College, Jawar, District Palagar. Dear friends, in the previous part of this online video lecture series, we discussed about the collision theory. We tried to explain, we tried to discuss the various postulates of collision theory which is important to explain the rate of reaction. And according to the collision theory, rate of reaction depends upon the number of active collisions between the gas molecules, and at the same time we tried to discuss the collision theory for biomolecular reaction, and we aware about for collision at least two molecules are required, and that's why here whenever the collision between the two molecules take place, definitely in that case this collision must have sufficient energy is equal or greater than the energy of activation. Then and then that collision is responsible to form the product, and such type of the collisions are called as the effective collision. So here one of the important assumption according to collision theory is that the rate of reaction does not depends upon the only number of collision, but actually it depends upon the number of effective collision. So here rate of reaction of gaseous substances is always proportional to the number of effective collision. So dear friends, today in this part of this video lecture we are going to discuss the collision theory for another type of the reaction called as unimolecular reaction. Actually here this is the important thing, because in the last part we discussed collision theory for biomolecular reaction, and now today in this part we are going to discuss the collision theory for unimolecular reaction. So first of all, to discuss, whenever we want to discuss the collision theory for unimolecular reaction, but before this we should know what is the unimolecular reaction. This is very important thing to discuss the unimolecular reaction, because we want to discuss the collision theory for unimolecular reaction. So first of all we will see what is unimolecular reaction. Unimolecular reaction, these are the reactions in which only one molecule of the reactant take part, and that type of the reactions are called as the unimolecular reaction. Whenever only one molecule of the reactant take parts in the reaction, then that type of the reactions are called as the unimolecular, because here this word uni means the single, uni means only one. So whenever only one molecule take part in the reaction, then the reactions are called as the unimolecular reaction. And according to the collision theory, we are already aware about for collision at least two molecules are required. So it is quite contradiction for unimolecular reaction, because in case of an unimolecular reaction only one molecule take part in the reaction, and for collision we require two molecules, or there is a requirement of two molecules, and in unimolecular reaction only one molecule take part in the reaction. So how the collision take place between in unimolecular reaction, which leads to the rate of reaction. So this is the important thing here, and based upon the same, because according to collision theory for collision at least two molecules are required, and hence the postulates of collision theory that the rate of reaction is given by the number of collision per second between activated molecules cannot be applied for unimolecular reaction, or cannot be applied to unimolecular reaction. This is the problem here, because for the collision there should be at least two molecules, and in unimolecular reaction only one molecule take part in the reaction, and that's why the postulates of collision theory that the rate of reaction is given by the number of collision per second between the activated molecules cannot be applied to unimolecular reaction, because collision theory involves the two molecules. According to collision theory, the number of collision per second between the activated molecule is deciding the rate of reaction, and within the single molecule collision is not possible. That's why this postulate cannot be applicable to determine the rate of unimolecular reaction, and hence the behavior of unimolecular reaction can be explained on the basis of what? Biomolecular reaction. So definitely here we want to explain the unimolecular reaction, but for that purpose we will take the help of we will take the help of biomolecular reaction. So here make one thing clear, we are going to explain the unimolecular reaction on the basis of biomolecular reaction. How, that we will discuss here. So Lindeman in the year of 1922 suggested that molecules acquire activation energy through the collision with other molecules. As a result, some molecules get activated. So this is the suggestion made by means of Lindeman in the year of 1922, and he has suggested that molecules acquire activation energy, or molecules acquire energy of activation through the collision with other molecules, and as a result the molecules get deactivated. Based upon the same, whenever we are going to discuss about the activated molecules, then these activated molecules, the water molecules get activated through the collision with other molecules. These activated molecules decompose only after some time lag, so they require some time. Then these activated molecules molecule gets decomposed to form the product, and hence there is some time lag between the activation and the decomposition of activated molecule. There is some time gap, there is some time lag between the activation of the molecules and decomposition of the activated molecule, and that time lag between the activation and decomposition is very important. When this time lag is very large, it's very important, and when this time lag is very large, then it is observed that many activated molecule gets deactivated. It's very important, not decomposed. Many activated molecule get deactivated. So this is just like the example, suppose we are waiting for someone, and we have arrived there. So there is a time gap, or there is a time lag between arrival and waiting. But if this time lag or this time gap between arrival and the waiting is very large, or it is quite larger, then it is possible that some of the people left behind back, and definitely this process is called as deactivated. In the same thing, when this time lag is very large, many activated molecule gets deactivated again through collision with ordinary molecule or less energetic molecule. So this means again energetic molecule becomes non-energetic, and hence the rate of reaction will not be proportional to. It's very important. And if this time lag is very large, then the many activated molecule gets deactivated through the collision with ordinary or less energetic molecule, and in that case the rate of reaction will not be proportional to the number of activated molecule. It is not proportional to number of activated molecule, because many activated molecule gets deactivated, and definitely the number of activated molecules goes on decreasing, and here in that case the number of activated molecule does not decide the rate of reaction. Here I hope you will try to understand what I want to say. This is the initial assumptions made by Mr. Lindeman in order to explain the unimolecular reaction, rate of unimolecular reaction based upon the biomolecular reaction. And here he stated that whenever the activated molecule decompose after some time lag, and if this time lag is very large between the activation and decomposition, then many activated molecules get deactivated. So there are both the reactions, activation and the deactivation, and if this deactivation gets started through the collision with ordinary or less energetic molecule, then the rate of reaction will not be proportional. It means it is not depends. It will not be proportional to the number of activated molecules. So how many activated molecules are present, that is not important to decide the rate of reaction, but it will be proportional to what? It will be proportional to only those molecules which retain their energy of activation. It's very important how many molecules can retain their energy equal to energy of activation in activated state. That number of molecule important, and that number of molecule will decide the rate of reaction, and that's why the rate of reaction will not be proportional to the number of activated molecule, but it will be proportional to only those molecule which retain the energy of activation. And when this rate of deactivation is much greater, then the rate of decomposition. It means that there is a forward reaction and the backward reaction. Rate of deactivation is the rate of deactivation is the rate of backward reaction, and rate of decomposition is the forward reaction. Means we can say that decomposition is responsible for the formation of product, while deactivation is responsible for the formation of reactant again. So I hope you can understood about this, because whenever here I can show you, suppose this is a reactant, this is the reactant, and this is the rate of, it gives the formation of product, then this reactant get converted to product, through the formation of an, or you can say this is nothing but the reactant, or this is suppose activated complex, and it gives the formation of what? It gives the formation of product. So this is the simple reaction. Reactant get converted into product through the formation of this activated molecule initially. So this is the rate of activation, this is the activated molecules. So whenever it get converted to product, so this is the rate of this is the rate of decomposition, and whenever this activated molecule again reconverted into reactant, this is the rate of what? This is the rate of deactivation. So whenever this activated molecule get converted to product, it will be called as the rate of decomposition, and whenever this activated molecule again reconverted into reactant, it will be called as the deactivation. And here the same thing that I am going to explain here. When this rate of deactivation is much greater than the rate of decomposition, then the reaction will be unimolecular. If the rate of deactivation is greater than the rate of decomposition, then the reaction will be unimolecular. It means that whenever the rate of forward reaction is much greater, whenever the rate of backward reaction is much greater than the rate of forward reaction, it will be simply unimolecular. I hope you will be able to, because this is activated molecule get converted into product, this is the rate of forward reaction, or it is called the rate of decomposition, and this activated molecule whenever reconverted into reactant, this is called as the rate of deactivation or rate of backward reaction. Here, in order to explain how the biomolecular reaction can be compared with the unimolecular reaction, or how the unimolecular reaction can be studied by compared with the biomolecular reaction. Here definitely the number of collisions are going to take place, but here the thing is that, so whenever this rate of deactivation is much greater than the rate of decomposition, means the rate of product formation, then the reaction will be unimolecular reaction. Here I hope you can understood. So whenever this rate of deactivation is much greater than the rate of decomposition, it will be considered as the unimolecular reaction, or the reaction is called as unimolecular reaction. So for that purpose, rate of deactivation should be greater than the rate of decomposition. So dear friends, based upon the same, the collision theory, we are going to discuss the collision theory for unimolecular reaction, and this is given by the Lindeman. Lindeman tried to explain the rate of reaction with the help of collision theory, but for that purpose he considered the biomolecular reaction. So here Lindeman tried to explain the unimolecular reaction with the help of biomolecular reaction. Definitely for that purpose, rate of deactivation is much greater than the rate of decomposition, and that's why the reaction is called as the unimolecular reaction. For that purpose, he has tried to consider a simple reaction in which the reactant get converted into product. Suppose this is the reactant, it get converted into product with some rate constant. Definitely here this is not the expected, but this is simply the case that A get converted into product, and this reaction according to the Lindeman, so this is the reactant which gives the formation of product, but according to the Lindeman, this above reaction takes place in number of steps, and in the first step the two reactant molecule collide with one another. So this is the one reactant molecule, it collide with another reactant molecule of the same type, and it gives the formation of an activated molecule A star, and another one is the reactant. So this A star indicated here, it is the activated molecule, and later this activated molecule indicated by A star undergoes decomposition and it gives the formation of products. So I hope how many steps are there. In the first step, the two reactant molecule collide with one another, gives the formation of what? Gives the formation of activated molecule indicated by A star. This activated molecule, some amount of activated molecule again reconverted into reactant. This is called as the rate of deactivation indicated by K2, and some amount of this activated molecule get converted into product. This is in K3, which is called as the rate of decomposition. So in the first stage, one reactant molecule A get activated into A star, and rate constant is indicated by K1. In the second step, if there is some time gap or the time lag, then this activated molecule gets deactivated and reverse process takes place with the rate constant. So rate of deactivation is K2 and the rate of decomposition is indicated by K3. K1 is the rate of formation of activated molecule, rate constant for the formation of activated molecule. K2 is the rate constant for the deactivation, and K3 is the rate constant for the decomposition. I hope you can consider all this type of the rate constant. There are three rate constant, K1, K2 and K3. K1 is the rate of formation of activated molecule, K2 is the rate of deactivation of activated molecule, and K3 is the rate of decomposition of activated molecule, A star indicated. So dear friends, based upon the same, definitely where people are interested to explain the rate of unimolecular reaction, how we can study the rate of unimolecular reaction with the help of Lindeman theory, but it requires the expression, it requires the derivation, and we will derive equation for the rate of this unimolecular reaction with the help of Lindeman theory with reference to biomolecular reaction. So here definitely it requires much more time. So we will stop here and we will resume in the next part to complete this derivation, to complete this study of Lindeman theory for unimolecular reaction. So thank you very much. We will resume in the next part to discuss the Lindeman theory for unimolecular reaction. So thank you very much.